Hi, kids! I am going to do a little instructional video on universal potential energy and hopefully make sure that you guys understand this okay. First thing, if it's universal, it means it works everywhere. So, make sure that you understand, guys, that if we are talking universal, near the surface of the earth, you guys understand potential energy. You go up higher, you have more potential energy. Well, that's going to be true universally. If you go away from whatever it is, if you're talking about the sun being the center of your system, if you're talking about the earth being the center of your system, whatever, as you go further away, you gain potential energy. Okay, but there's a reason we cannot use this equation for universal potential energy. A couple things. Well, number one, G is not constant. Okay. Hopefully you guys understand that the acceleration due to gravity, the gravitational field strength, it changes as you move further away. And second, when we're talking universal, you don't get to pick what you want as zero. Near the Earth's surface of the Earth, you get to decide. Well, I'm going to call the tabletop zero because it makes it convenient for this problem. Universally, you don't get to do that. Now, again, the reason that you get to call whatever you want zero is if you look on your formula sheet right about now, you can see that really what's important is the change in potential energy is what's important. And because that's the case, because the change is what's important, that's why you can use this formula. When we are talking universal, that really what's happening here is, remember, potential energy only is part of your system if gravity is part of your system, if you're including, for example, the earth or the sun or whatever. So if your system includes gravity, then potential is part of your system. So the only way to have potential energy is to have gravity. Well, that means universally the only place in the universe that you have no potential energy is the only place in the universe where you have no gravity. Well, where is that? Well, that is going to be when you are ridiculously far away, okay? A lot of times we'll call that R equals infinity. Really what that's just saying, we're so far away from our object, to the earth, the sun, or whatever it is, that essentially it has no force of gravity. If there has no force of gravity, then it has no potential energy. So that's what we're talking about universally. The other way to think about it, and hopefully you guys saw the spandex demo, but let's pretend down here is where the Earth is. Okay, you can really truly think of this gravity well. Okay, like this is your energy well, so that if you are down here near the surface of the Earth and you want to escape, well, you need to get out here. And remember, this is your R equals infinity spot. This is where you're ridiculously far away from the Earth. Well, at this point, my UG equals 0. Why does UG equal 0 at that point? Because I am ridiculously far away. So that, so otherwise it is not equal to 0. I'm super far away. There's no gravity. There's nothing there. So if you guys take a look, if there's ever a question where it's like, hey, what's the escape velocity of the Earth? Really, if you were to draw your picture, it'd be like, hey, here's the Earth, here's your spaceship, and it's trying to escape the Earth, okay? If my spaceship is trying to escape the Earth, it needs to be moving. So really, hey, my spaceship is down here someplace, and I have to move up there, okay? Well, so this is my point A, and my point B is going to be where I am ridiculously far away. Point A is down here, point B is up there. So if you look, if I go from A to B, what am I starting with? Well, I have potential energy. Oh yeah, I have potential energy down here. And what do I have? Well, I have kinetic energy, because good luck escaping anything if you're not moving. And then as it moves up, and again, I just want to know what is the velocity I need to go to escape. So I'm not applying any outside force. Well, if that's the case, well, geez, on the way up, it's going to slow down. You can think as it goes up this hill, or if you guys saw the spandex demo, it's going to slow down, and eventually this would be 0. And again, we're finding, if you're finding the escape velocity, this is the minimum speed that you can have. If you're actually like a NASA scientist, I don't want my spacecraft to get to r equals infinity and stop. I want it to keep going, but this is escape velocity is the minimum you can go. So, hey, at this point I have no kinetic energy. Well, at that point I have no potential energy. So at that point I have no energy. And you might go, wait a second here. How could this plus this give you nothing? Well, that's because this is where U equals 0. And down here I am underneath 0, which is why it's negative potential energy, which is why your equation, if you look, everybody see it down there, is actually no, okay? Which is negative. And then you would just plug stuff in. It would get negative GMM over R plus 1/2 mv squared equals 0. And then you could do some math and you could solve that for your escape speed. In this case, the mass of my rocket ship would cancel out, and then you could go ahead and solve. But if you had something like, if you were on the moon trying to escape the Earth, well, the moon is more here. So you can see it's going to be easier to escape the Earth. Because I only have to go from here to here. Where if I had something like the sun, well, the sun is going to have a gravitational well that's going to be way deeper than the Earth. And so, like, if here's the sun down here, I got to go a lot faster to escape the sun. Where if I am trying to escape the moon, maybe my gravity well only looks like this. Where if this is the moon, I don't have to go near as fast to escape the moon. So anyway, I hope that helps. Bye, kids.